Okay, so what do you guys know about exponents? You guys have worked with them at some point in math before, I'm sure, right? Do you guys know that, I feel like this picture shows here that x times x times x times x is x to the 4? Okay, why is it not 4x?
4 times x, not 4x.
Okay, well, 4 times x is 4x. There's another way that you could write out 4x, though. And it does involve 4 x's, but it would be this. X plus x plus x plus x. That is x that you get to add to itself 4 times. Does that make sense? I want to make sure everyone's clear on that distinction. X times x times x times x. That's x to the 4. And the big difference here is that, how do I put this? We can draw x to the 4. Like if I was giving you y equals x to the 4, you guys know how to draw that graph because we did it in like our first unit. What we're going to do now is we're going to flip the bottom part and the top part. In terms of terminology, this number down here is referred to as the base, and this top number up here is known as the exponent. What we're going to do now is we're going to flip the base and the exponent. And I'm going to ask you guys to graph y equals 2 to the power of x. That's where we're going to start. What does y equals 2 to the power of x mean then? I'll just rewrite it down here. Y equals 2 to the power of x. Well, it means start with 2 and times it by 2, times it by 2, and keep timesing. When am I allowed to stop, guys? When the number of 2's equals x. Do we know what x is? That's the problem with exponential functions, is unlike the graph y equals x to the 4, where I know that I do x 4 times, and then I get to stop. When you do 2 to the power of x, we have no idea how many times you're going to keep multiplying. Does that make sense? And so it depends on what x is. If x is 5, then you'd have stopped right here. If x is 1,000,000, well, 2 to the power of 1,000,000 is going to be a very large number, obviously, because you're timesing 2 over and over again. Does that make sense? Okay. Before we get to that, then, I guess I started with my first question. You guys should know something about exponents from previous grade levels. So let's just do a quick review of some of the rules that there would be. If I gave you, let's just go with regular variables as the bases. So like if I give you x squared times x to the 3rd, do you guys know that would be x to the 5? Is that something that you're familiar with? If you're not, let's just go through the reasoning why. This is x times x, and then this one is x times x times x. So by the time you're done, you have 5 of them. Does that make sense? Dividing means subtracting. So if you had x to the 3 over x squared, it's like having x, x, x on the top, x, x on the bottom, and you can cancel a bunch of them. And so by the time you're done, you're left with x to the 1, which is what 3 minus 2 is. That familiar? Okay. Power law would be something like x to the 3, and then you square the whole thing. Well, what that really means is you have x to the 3 times by another x to the 3. So here you have 3 x's. Here you have 3 more x's. So altogether you have 6 of them. The rule here is you have to times those numbers. Does that make sense? This next one, in my opinion, is probably the one where if someone's going to make a mistake, this is where they'll make the mistake. Let's say that I gave you 2x squared. So you have something and something else, 2 different pieces inside. This is not equal to 2x squared like that. It's actually equal to 4x squared. Because this squared right here applies to the x, and the squared right here also applies to the 2, meaning that 2 times 2 is that 4 something. Does that make sense? And the last thing also applies if you've got, like, say, x over 2 all squared. That would be equal to x squared over 4, because you'd have to square the 2 to get 4, and you'd have to square the x to get x squared. Is that...
Sorry, what was the last one?
Okay, so like if you had x over 2 and you squared the whole thing, you have to make sure you square the x, so that's this x squared right here. But don't forget you got to also square the 2, which is why I made it a 4. Are those things you guys are somewhat comfortable with? Okay. This would be a good example of where I'm going to spend one slide on it. You guys have done this, I know, at some point in your lives. You still need to have those skills, though, because if you screw up those skills, you're going to get all these questions wrong. So. Okay, so let's start off by sketching a graph of y equals 2 to the x. So like I've been kind of hinting at, the change here is that the base is a number, an integer, I guess, and the exponent now is actually the variable. And I'd like to do this without a calculator, at least at first, just to kind of walk through the process. So let's do...
Oh, it's okay, it's not safe.
Oh, it's just totally out of order?
Yeah.
Sorry, guys.
Yeah.
Way out of order. Alright, let's switch. Everyone okay?
Yep.
Okay. So give me a number for x.
4.
Sure, let's start with 4. I'll put it way down here if that's okay, because there's numbers before 4 we should also try. What is 2 to the power of 4? 2 times 2 is 4, times 2 is 8, times 2 is 16. 4 might have been less applicable because I don't think I can graph this. 4 16ths up there. Let's start with 0. 0 is actually probably the most purposeful one. Does anybody know what 2 to the power of 0 equals? It is 1. There's a rule you need to know if you don't know it already. Anything to the power of 0, anything to the power of 0 is always 1. Basically, it's like me saying, you're going to write 2 no times. So it's like, I'm going to ask you to write out some 2's, and then you're going to say, well, how many times should I write 2? And I'm going to tell you, actually don't write out 2 at all. What's left? Well, technically it's like there's a 1 multiplied by all of that then. Does that make sense? So anything to the power of 0 actually is 1. So I can plot that right here. My y-intercept is at 1. Let's try 1. What's 2 to the power of 1? 2. And what about 2 to the power of 2 and 2 to the power of 3? Let's write those ones out here. 4 and 8 make sense to everybody? So 2 to the power of 1 means that you go with 1 and 2. 2 goes up to 4. There it is. And 3 goes up to 8. To start off with, this graph kind of has the shape of a parabola. Kind of. Like, it's not exactly. But would you guys agree that it's kind of got at least half of a parabola right here? The negatives is what completely changes things. Is this graph does not actually go on the other side. There's no vertex over here. Let me just keep writing these out here, though. 1 gave 2, 2 gave 4, 3 gave 8. Okay, you guys can grab your calculators for this if you need. Let's try minus 1. What happens if you do 2 to the minus 1? Anybody know?
1/2.
It is 1/2. It's been a while, but I know I showed you guys these rules. Anything that has a negative exponent is actually on the bottom of a fraction. 2 to the 1/2 actually means 1 over 2 to the 1. So that's 1/2. 2 to the minus 2 then means 1 over 2 to the 2, which is 1 over 4. 2 to the minus 3 then is 1 over 2 to the 3, but 2 to the 3 is 8, so it's 1/8. What is happening to these numbers as I make the exponent further negative? They're getting much smaller, yeah. So what ends up happening is this becomes half, this becomes quarter, this becomes 1/8, 16th, 32nd. What's happening on this left-hand side of the graph? Anybody know? Good. It's creating an asymptote for anyone else who said that. This is getting very, very, very close. I didn't draw it very well there, but there is an asymptote here where y is never capable of equaling 0. So what you get is a very flat graph for the longest time. And then all of a sudden the graph just takes off. And maybe you've heard the term, it starts multiplying exponentially. We use that as like a verb, adjective, I don't know. But like it's a saying people would say, is like it takes off exponentially. This graph is very, very slow at first. And then all of a sudden, shoots up there. This is an exponential graph. So my goal today is to walk you guys through different sorts of exponential graphs, how we can move them around, what they would look like, talk about their properties. And then the biggest part of this section is that you're going to get asked word problems. Yeah, that's the look. No. So my goal is to help you get ready to be able to solve some word problems. I find them frustrating because I don't know what the word problem will be on. So I kind of need to be ready for anything. So, okay, let's talk through these properties. Is there an x-intercept? There isn't, actually. By definition, this exponential graph can't have an x-intercept because you can't somehow make this get as low as 0. I know I kind of drew it as though there was one, but there isn't. Where's your y-intercept? Yeah, 0, 1. Right here. There is an asymptote. We just wrote it out. Y is not able to be 0. You could write it with an equal sign or a not equal sign. I think both are kind of conventionally allowed. The domain, you can actually use any number you like for x. That's not a problem. However, the range is limited to slightly less than half of the graph. I said slightly less than on purpose. The lowest number you can use is 0, but you actually can't use 0. That's why I used like a curl bracket. But it can go as high as positive infinity. This is one way of writing range. The other way you could write it is y is greater than 0 and just don't put the little bar there. Both of those will work. So far, so good?
If you were writing the range on the diploma, would you have to include the little positive sign?
No, they probably wouldn't skip the plus sign.
Okay.
Yeah. I mean, if you had it or you didn't have it, that's probably okay. So let's try another one. I'm going to go through this one a little faster. We're going to do 3 to the x. And I'm only going through this process to show you the very, very slight differences. There are very few differences, actually. So I'm just going to do an xy table of values again. And I'm going to go from -3 all the way up to 3. 3 to the -3 means 1 over 3 to the 3. Good, it's 1 over 27. That's essentially 0. It's not quite 0, but boy, it's not close to 0. 3 to the -2 is 1 over 3 squared. That's 1 over 9. It's slightly more, but I mean, a 9th is basically right there. 3 to the -1 is 1 over 3 to the 1, so that's just 1/3. So that's right there. What about 0? 3 to the 0? By definition, anything to the 0 is 1. Okay. Here's my first point. The y-intercept of this graph, the exact same.
Most likely, almost always be the exact same.
Most likely. Now, I will show you examples where we can change it, but at least for the first few examples, like a very simple graph like this, it should be a 1. But we can mess around with that, though. 3 to the 1 is 3, 3 to the 2 is 9, and 3 to the 3 is 27. Hopefully I didn't go too fast there. So if I plot that, you get a 1 with 3, you get a 2 with 9. 3 with 27 is already off my graph. So showing you a picture of what this looks like. How different is it than the last graph? Not very. Most exponential graphs, at least if they're very basic exponential graphs, they should look almost the exact same. I mean, are they quite in the exact same spot? No. I mean, I guess the other graph was a little bit lower. I think the other graph was like, say, here and here and here. So the other graph was a little bit slower than the other graph is. But in terms of your properties, they're the exact same. There is no x-intercept. Your y-intercept is at 1. You still can't let x equal or y equal 0. X can be anything you want. Y has to be bigger than 0. So for the most part, if you get like any whole number right here, even if you get like 3.5 or 7/2 or something like that, the graph is going to take off in kind of an upwards trajectory. Here is a graph, however, that has similar properties but a very different look to it. And I think to save time, let's do this one on our graphing calculator, because I don't want to take too long on this. So grab your graphing calculator, and let's go y equals 0.5 to the x. So to type that in, it would look like 0.5 power x. It is. It's backwards. We actually might have talked about this at some point in a physics or chem class. The first graphs that I showed you, we would call them growth. This graph here, anybody know what we would call it? You want to see it in the notes coming up later? It's called decay, actually. For those of you guys who took my physics class, we talked about like radioactive decay. It often fits graphs that look something like this. Like half-life, yes. Yeah. Half-life is applicable to this. So the basic idea is it still has a y-intercept right here at 1. But rather than the graph getting bigger and bigger and bigger because you're timesing by 2, timesing by 2, timesing by 2, you're actually cutting things in half, cutting them in half, cutting them in half. So what will happen here is this will get cut in half, and this will get cut in half, and this will get cut in half, and this will get cut in half. And so the further you go on in x, the smaller it gets because you're cutting things in half. Okay, so let's show those out here. If you do 0.5 to, like, say, the power of -3, what that means is it's 1/2 to the -3. Does that make sense? Well, if you guys remember much about the negative exponents means that you make it 1 over top of something. But what happens if it's already 1 over top of something? Flip it back to normal. So this actually means rather than making it 1/2, it's actually 2 over 1 to the power of 3, which makes it 8. Test it on your calculator if you want to. Like take 0.5 and go to the, don't do absolute value, do 0.5 and go to the power of, like, say, -2. It makes it a bigger number, like a big whole number. If you do 0.5 to the power of -6, it actually becomes quite large. The negative takes the 0.5 and rather than treating it as a half, actually treats it as like a 2. And the 6 then times this 2 over and over again. So what ends up happening is this graph looks like this. It starts high and drops down rather than starting down and dropping high. Does that make sense? Rising high. The properties, however, are the exact same. The properties do not change. You still have no x-intercept. Your y-intercept is still at 1. The asymptote, well, you still can't let y equal 0. Your domain is whatever you'd like it to be, and your range is, again, just bigger than 0, but not included. So, essentially, there's 2 main types of exponential graphs. The terms we use are growth and decay, which I think is probably what I have in my next few slides. So maybe you can find this one somewhere. This one right here is growth. Actually, there's 2 graphs here. The green one is 8 to the x. The blue one is 2 to the x. I mean, you can see the 8 to the x one just takes off a lot faster, that's all. Whereas the red graph is decay, which you might recognize if you did physics. That's like half-life kind of graph. I think I have slides in here just kind of referring to how this is useful. Often if you have, like, say, population graphs over time, population graphs usually rise exponentially. To be honest, most of the time, if you're talking about finance graphs are intended to rise exponentially because you'd like your money to keep growing faster and faster and faster. Like if I was some sort of high-powered marketing executive and I had like fancy graphs in a boardroom, you'd like to show the graph that's green and say, hey, look how much money we're making you. Does that make sense? You wouldn't want definitely not a decay graph. That means you've done poorly.
What is exponential?
So basically, exponential is this shape where it starts low and it does this. Technically, exponential could also start high and go down. Typically, if you were like a money-making person, though, you wouldn't want that. There's actually a lot of application, though, to anything that's exponential, either growth or decay. I think I still have one more slide here with stuff on there. Linear graphs go up at a steady rate. Exponential graphs, they don't go up steady, they go up like fairly steeply. I don't know if that makes sense. Okay, let's try graphing this in our graphing calculators. We're going to try graphing -2 to the power of x. So go bracket, make sure that negative is inside the bracket. -2, and then go to the power of x. So I've already shown you how to do a graph that uses whole numbers. I've also shown you how to do a graph that uses like a decimal number. What if we try to do a graph that involves negative numbers? What would that look like? So I try graphing it. I don't know what your calculator is going to do, but it might do something like mine, where like literally there's nothing there. And maybe you can go to your table of values, and maybe you should change your table set to start at 0 again. And as you look at your table of values, you say, hang on a second. There's points literally everywhere here. It tells me there are points there. Clearly, 0 and 1. And I go back to the graph here and I go, where's the graph, guys? You guys have the same problem?
Yeah.
Okay, look at the points. There is a huge problem here. It goes 1, -2, 4, -8, 16. If I were to plot those, it would go like this. 0 would go with 1, like we've had before. Then 1 would go to -2. 2 would go up here to 4, then down to -8. This graph does not do this. That's not what's happening here. Why am I seeing numbers here? Well, because this is only doing whole numbers. I want to change my table set. And rather than, you see how this number here goes up by 1s? Have I shown you how you can mess around with that and make it so it doesn't go up by 1s? Let's make it go up by 0.1s. This will make my point. You see I'm getting some errors in here? You cannot, for x right here, you cannot let x be like a, how do I describe this here? Well, let me just test some numbers here. If I do -2 and I go to the power of 1, that works. But let's say I try to go -2 to the power of 1.239. That doesn't work.
Why?
Okay, so let's talk through what you're doing when you're putting a number there. If you put a 2 up there, you're doing -1 times by itself. Does that make sense? Well, a negative can times by a negative. But it doesn't necessarily work to take that and times by 0.2 of itself. Does that make sense? So here's the point I want to make. We cannot actually make a graph where this is negative. We don't even bother trying. Even though your calculator makes an attempt to, this is not really considered to be a function we can work with. Okay. Do you guys know the terms discrete and continuous? We've used them last year. A continuous function means that like you can use any number you want. You can use 1.1, 1.2, 1.3, 1.00001, 1.00002. That's a continuous function where you can use any decimal number in between. Discrete would be where like you can only use like say whole numbers. This right here would be a discrete function. Yes, it kind of works, but you just get dots everywhere. You can't actually connect them with a line. Maybe the best example would be shoe sizes. I can buy my shoes in either 10s, 10.5s, or 11s. But I can't actually buy a shoe size in 10.973s. Does that make sense? So, long story short, the point I want to make here, we cannot do this if there's a -2 right there. Okay. At least we can't make it a continuous function. Yes, there is actually a function because clearly we graphed it, but it's screwy. So, sound good? Okay, so quick summary then of what we've talked about so far. Whoa, I just saved this thing. It's okay. Exponential functions typically have the form like this. It's f of x equals a times b to the x. And that might look different than what I've done so far. Because so far I've given you, like, say, y equals 2 to the x. What number was right in front of this here? Yes, good, a 1. Drianna, I think you were the one who asked whether the y-intercept is always at 1. Now I'm going to start showing you how to change things. Because if I gave you the graph y equals 3 times 2 to the x, what's going to happen is when you plug in a 0 for x, this section right here would become 1, and then you would times it by 3. And so what you can actually end up happening is you can stretch a graph upwards. That 3 there would be a stretch.
So are these, we're going to have different rules for this kind of stuff?
We're still going to use all of those, like flipping them upside down, sliding them over. We're still going to do all of that stuff too. But I would say typically we write them as a times b to the x. A is what, like, stretches it up and down. So if b is greater than 0, there's 2 possibilities. So by b being greater than 0, I mean you can't use a negative number. I just showed you negative exponent things don't work. So if b is bigger than 1, it goes upwards. And if b is a decimal number between 0 and 1, it comes back downwards. Okay. This last line is where I want to go then. We can translate, reflect, and stretch all of these graphs as well. So let's show you how that looks. I don't actually want to do anything here. I just want to show you some pictures. See if you can find these pictures here. Let's find this one. I probably have 1, 2, 3 slides of pictures somewhere in here that look like those. So here's the first one I want to make a point with. Do you guys see how in blue right here I have 3 to the x? That's a standard graph. The number in front of 3 to the x is 1. We just didn't write the 1. Over here in red, I put a 4 in front of it times 3 to the x. What this means is take 4 and times by 3 and times by 3 and times by 3 and times by 3, and I don't know how many times I'm timing by 3. What it does is it takes the graph and it stretches it upwards. So my y-intercept is no longer here at 1. My y-intercept is now up here at 4. This 4 right here has become my y-intercept. Or, see this guy right here, I still have 3 to the x, but I have a minus 2 in front. The minus takes the graph and flips it upside down. So now the graph is going below the axis the whole way, and the 2 has stretched the graph further up and down. Technically, there's not really anything up to pull, so it just pulls the whole thing down. So that's why my new y-intercept is right here at minus 2. Does that work? Okay, more pictures. What if I were to then put, like, say, a 3 in front of the x? This one right here, if you can't read that, is 2 to the 3x. Well, a 3 directly next to x takes the graph and squishes it in. So hopefully you can see how this blue graph right here, compared to the red graph has actually been pushed inwards. That makes sense? Or this guy right here, if you can't read that, that is 2 to the negative 0.5x. The negative right in front of the x flips the graph like side to side. So now rather than it being a growth graph, it actually made it a decay graph. And for the last step, a 0.5 actually takes the graph and pulls it outward. Last thing you can do, you can also literally add like a +2 or a -3 afterwards. This one's probably the most unique. It changes a lot of things. It's going to change your y-intercept. You see how your y-intercept right here used to be at 1? But if you throw a +2 afterwards, your y-intercept's up here at 3. One more thing though, it also changes your asymptote. I like this picture because I think it shows it. Your asymptote used to be right here at 0. If you throw a +2 afterwards, well, your asymptote's up here at 2. Does that make sense? Or if you throw a -3 afterwards, your asymptote's down here. And then last thing, if this was like, say, a 6 to the power of x with a plus 2, it's just pulled the graph backwards.
So it's just like almost.
It's all the same rules, it's just we're now using those rules on exponential graphs. So, I've achieved more or less my goal. I've talked to you about how exponential graphs work. Now let's see that you guys can figure out what this will look like without using your calculator. So, where do I start? Sure, that's not a bad place to start. Where's the asymptote going to be? Yeah, we're going to move this whole thing up 2. There's an up 2 right there. So maybe an asymptote at plus 2. That's a good place to start. Okay. This 2 right here, was this graph supposed to be growth or decay? It was supposed to be growth. So normally my graph would have done, don't draw this, but it normally would have done this. But we're changing it around quite a bit. What is this minus 3 going to do out front? So before I even moved anything, my graph would have been like this. Then my graph would have been upside down. But not even just upside down. I want to focus on one key spot. This is where the y-intercept would have been if I flip it upside down. But the minus 3 would then make it go to, like, say, right here. You'd have an upside down graph that has a y-intercept at minus 3.
But that's off the 2. So
But I haven't accounted for that plus 2 yet. Well, we got to go back up 2, though. It's not down 2.
Which one makes it upside down here?
The minus right here. That minus flips the graph upside down. The 3 stretches it. Sean, I think you're backwards, though. This plus 2 takes this graph. And I can do this because I've got my smartboard. But I'm literally going to pick the whole graph up. I'm going to shift it up to there.
oh, okay. So
Where's my y-intercept back to? Back at 1. The minus 3 took my y-intercept, made it go into the negatives, made it go into the negatives by 3. But then the plus 2 brought it back up from negative 3 back to negative 1. So this right here is what my graph should roughly look like. So let's talk through properties. Is there an x-intercept? Yeah. You can't always default to x-intercept not existing. Now, at least for right now, we're going to show you how to algebraically solve for the x-intercept in a little bit. But would you guys be able to find this using your graphing calculator? Okay, so I'll just put a little note here saying there is one. It exists. Find using calculator. Eventually, I'll show you guys how to actually solve it algebraically, but we're not to that point yet. But clearly, there is an x-intercept right here. Y-intercept? Oh, we just said it was a negative 1. The asymptote, y cannot now be 2. And that's really based purely on this number right here, that 2. That tells you where it's at. Your domain is actually anything you want. You technically still can plug in anything you want for x.
When would it be where you just, like, where it can't be an algebra?
Mm.
What would be an example?
Well, we have some of those when we did our square root graphs and our fraction graphs, but to be honest, for like an exponential graph, it's anything you want it to be. When we eventually do logarithms, though, logarithms also have restrictions on them. So I would say in terms of the graphs we've covered, square root graphs, be careful of, because you can't square root negative things. Fraction graphs, you have like little gaps in the graph because you can't have like sometimes we write it as like a 0 to 2 union 2 to positive infinity, where it's like literally you can't have the number 2. But for these graphs here, though, you can have anything you want for x. And then for range looks like, no, that's x, we need y. Y has to be less than 2. Sound good? Okay, why don't we take a break? I've achieved outcome 1. Outcome 1 is basically, do you know what an exponential graph looks like? That's not probably all that hard. Most of the questions on your assignment then are going to be in one of 2 categories. Category 1, I'm going to give you an equation, I'm going to ask you to graph it and tell me about it. the harder part of this unit, you're going to get a bunch of word problems. And so that's where I want to finish up with after our break here. A bunch of different word problems that we need to be able to use our knowledge of graphs to be able to solve. Does that make sense? So go take 5, and then we'll finish the word problems when you come back. Wait, so I threw you guys' assignment in front of you. If you guys just want to look it over, first thing is the due date is not until like next week Friday, so you've got a week and a half to work on this plus. So you should have some time. If you look at the questions, question 1 and question 2 are basically the exact same kind of question. I want you to sketch the graph and find the domain and range. For 2, I just said sketch the graph part. But basically, I'm asking you, like, can you tell me about a whole bunch of graphs? Okay, that's pretty straightforward. 3, we're going to have to do later. Like, my goal over the next few days is to give you some more algebraic skills on how to deal with things that have exponents. But the next section after that, if you look, like questions 4, 5, 6, 7, 8, 9, they're all word problems. I can pretty much guarantee on the diploma, you guys are going to get a couple of word problems that have to do with exponents and logarithms. And I find it frustrating because I don't know exactly what their word problem is going to be about. Does that make sense? So I kind of need you prepared for everything. I need you to have good problem solving skills.
How many word problems will there be?
Probably 2. It's 2 out of 40, but it's 5%. So I mean, you know, I would probably say about 2. So here, why don't I actually just show you guys the curriculum outcomes while we're talking about this. Just bear with me for a second to find them. Curriculum 30-1. Here's one of them. I don't know if you guys can see this all that well. Number 9 here, it says, can you graph and analyze exponential and logarithmic functions? It's fairly broad. But we've actually just talked about how to graph exponential functions. And to be honest, analyzing them means, like, can you tell me domain, range, x-intercept, y-intercept, asymptotes, like all that stuff. Right? So that one's not the hard one. There should be another outcome sitting down here. There it is. And again, it's very broad. Solve problems that involve either exponents or logarithms. So like I said, I need you to be able to solve a problem. What that problem is, I don't know. So my goal is to get you ready for a bunch of different types. Fair enough? So let me show you some word problems. Here's a biology overlap with exponential functions. Bacteria, fruit flies would even be another example. They usually multiply in an exponential manner. Yeah, they are, aren't they? So imagine that bacteria triples every 25 hours. Any ideas how we can fit that into an exponential equation if stuff is constantly tripling? Ignore the 25 hours for right now. How can I deal with the tripling? 3 to the x. That's where you'd start here, is that it's 3 to the x. Because stuff is tripling over and over and over again. Does that make sense? Now we have to deal with the 25 hours. It may just be best for me to show you how to deal with the 25 hours the very first time, because it's tricky. This is how you do it.
Why?
Okay, so let's talk through why I did that. Let's say that it's been 1 hour. After 1 hour, should it triple? No. 1 divided by 25 is not enough for it to triple yet. But what happens if it's been 25 hours? 25 over 25 is 1, which means that this 3 will happen once. What happens if it's been 50 hours? Well, we'd know intuitively, hopefully, that in 50 hours, it should double twice. So that means we want this number to be 2. Well, 50 divided by 25 would be 2. So that kind of gets us started. Let me just rewrite it again, though, because I want some more room here. Y equals an A value, which I haven't gotten to yet. Then it's going to triple, and it's going to do that every 25 hours. But I've missed an A value. What happens if we do nothing? What happens if time is literally at 0? What is 0 divided by 25? It's 0. What is 3 to the 0? 1. But we didn't start with 1 bacteria. We started with, that's what this number here is. Being able to write an equation, I can't really give you like a always do this, unfortunately. But I can hopefully give you like some good problem solving methods as to what would probably work. 1,000 right here, this refers to how much you start with. You start with 1,000. The 3 right here refers to the fact that you're tripling the bacteria all the time. And then x is your exponent, but I'm dividing by 25 because it takes 25 before you actually even triple for the first time. So there we have an exponential function. Can you guys see why this can be frustrating though? Okay, so first question then. How many bacteria would there be in 4 days? Good start. 4 times 24 is, what was that? Thank you. Where's the 96 go though? It's on top of the 25. It's x. Yeah, I guess in my equation right here, I should really be clear here. X is referring to what, like time in hours, I guess? And y is referring to bacteria. Does that make sense? So to answer this, y equals 1,000 times 3 to the power of, I'm going to put it in brackets here, 96 over 25. You can just straight up type that in your calculator if you want. I would not expect to be able to do that in your head. I can't do that in my head, that's for sure. So just make sure you don't screw up all the brackets. I guess I can guesstimate what it is. I mean, it should be 1,000 to start, 3,000 after 1 day, 9,000 after the next day, 27-ish thousand maybe. So 1,000 bracket 3 close bracket to the power of new bracket 96 over 25. What do you guys get? Yeah, that's what I got too. Like 67,943. You guys able to get that? Awesome. Okay. Good there? Okay, one more thing here. And then the question is, how many bacteria were there 3 days before the initial count? Well, not -3. Remember how days are 24? But you're going to do -3 times 24. So that's 72. So we got to throw in a -72. So that would be y equals 1,003. But then negative because we're kind of going back in time. Often, so far, whenever I've given you guys word problems, we kind of assume, well, you can't go backwards in time. But maybe in this one here, we kind of can and say, well, what would it have been in the past? So then it'd be 72 over 25. I got 42 basically. That makes sense? Okay, you first.
This was a numerical response on a diploma. They put a decimal wrong.
They probably would tell you what to round it to. They would have to in a question like this. They'd tell you round to the nearest bacteria.
Yeah.
I mean, I think logic would dictate you can't have half a bacteria. So you probably have to round it to the nearest whole number, but they should tell you that.
Okay.
Is that over 25?
That was over 25, yeah. Sorry. We're writing at 25. So I would suggest, in my experience doing exponential and logarithmic functions, most kids, their biggest struggle is can you write out the equation, like step 1, part A. Because once you have the equation, plugging numbers into the equation is not the hardest thing to do, probably. Does that make sense? Most of the time, kids' biggest struggle is, can you actually write the equation properly? That's the hard part. So let's try another one here. Oh, by the way, I have a bit of a secondary slide here. If you're ever working with like time, it's kind of confusing here, but usually this little exponent right here is actually written as like x over 25. Typically, like, this exponent up here actually has like a divided by piece to it, with the bottom number of that exponent being the 25 days. Does that make sense? That's kind of what I'm going for on this slide. Is often it's written as 3,000, that's A. And then B would be 2. And then the exponent is actually x over 5. What this information here means then, you started with 3,000. 2 means you're doubling. How often do you double? Every 5 days you double. Does that make sense? So this is typically how things get written with a fraction up there. I don't know if that helps at all, but let's try another example. You have a cup of water. It's heated to 100 degrees Celsius, and then it cools down to 20 degrees Celsius. The temperature is measured every minute, and they're plotted, and it's found that the water temperature decreases exponentially at a rate of 25% every 5 minutes. We need to first write an equation. This is the hardest part. Any idea where to start? What's that? We are going to need an x over 5 because it said every 5 minutes. So that's not a bad place to start. Hey guys, anybody want to do? I'm going to take a good work real quick. Thanks, guys. What was that? That's going to be my next question here. Could you close the door? Thank you. Okay, so Sean asked a really good question. How do I deal with the 25%? You sound like maybe you have a thought?
Would that be the coefficient?
Well, it's going to be the base. The base is 25. Well, it's not 25%. It says it decreases at a rate of 25%. Maybe I should just show you what number. Nope. It's that. Why? Because that's what you have left. That's a great way of phrasing it. If you're decreasing by 25%, it means you're keeping 75% of what you have.
So how, like...
Does that work? Yeah. So we've got the start of it written. This right here means you're keeping 75% of what you have. And in keeping 75% of what you have, it means you're losing 25. Okay? The x over 5 means that every 5 minutes, when x is 5, it gets losing 25%. I've also got to throw one more thing on here, though. It says that the air temperature is going to end up at 20 degrees Celsius. There is going to be a plus 20 at the end here. We need an asymptote at 20, because what's going to happen to this graph here is it's going to start way up here real high, and it's going to slowly but surely decrease. But eventually, it's no longer going to get any lower because 20 degrees Celsius is going to be the spot that it kind of sits at. Does that make sense? So it means that plus 20 needs to be my last number. There's only one problem with that. If I make 100 be the coefficient, 100 would then add to 20 and mean my y-intercept would start at 120. Yeah, I think 80 is the number I should use. Now that seems kind of odd. But let's try graphing this now and see whether this fits all the parameters we're looking for. So feel free to grab your graphing calculator. You guys know how on your last test I gave you a couple questions where you kind of just had to like try and mess around until you got an answer? That's kind of in preparation for this. You kind of just need to play with it until you can get an equation that works. So.
How do you know when you get an equation that works?
Well, make sure it fits all your parameters. Right? So make sure that everyone, once you look at the graph, that it fits everything here. So I think we need to start with an 80, because if I start with 100, it'll be too high. We need to make it go down by 0.75 to the power of x over 5. And then when we're done that, we need to add 20. Cross my fingers, hope I got this here. You need to change your window, though, for sure, because a 0 to 10 window won't work. So what is x referring to? Time, I guess. Why don't we go from 0 to, I don't know, maybe 30 minutes? It's half an hour. Should be enough to start. In the y direction, let's go from 0 to, it needs to go at least past 100, so maybe 120. Is this doing what I'm expecting it to?
Yeah.
I think so. Let's test a few parameters. Second, calculate the value when x is 0. What do I expect this number to be? 100. Good. It starts at 100 like I'm expecting it to be. I'll go table set. I'm going to make the table go to like a very large number. And then I'm going to look at the table and say, what's it happen to be after 10,000 minutes? 20. That kind of fits, doesn't it? Because it should be 20 degrees Celsius by the time it's done. And then one more thing, I'm going to go to my table here, and let's do it at 0. This may not work out quite as well as I'd like it to, but is this thing going down exponentially? Yeah, I guess in the way I'm looking for it, it is. So, does that make sense? Okay, so now let's answer our question then. Describe the translated, reflected, and stretched parameters. What does the 80 do to the graph? Stretches it up 80. What does the plus 20 do? It lifts the graph up 20. This one right here is probably the trickiest one. What does x over 5 do to the graph? So, but how do I put that into like stretching kind of vernacular? It's almost like you have 1/5 of x. What does a 1/5 do if it's directly next to x? Does it squish it in or pull it out? It is, yeah, it's pulling it out. So in terms of vernacular, like how you describe this in, I don't know, people words, 80 means make it 80 times taller. The 20 means move the whole graph up 20. And this x over 5 is really a fancy way of saying 1/5 x. 1/5 x actually means you're pulling the graph out 5 times 1. Which is why this happens every 5 minutes, not every 1 minute.
So if it was 5 over x, would it be making it thinner?
Well, I wouldn't say 5 over x, but if it was, say, 5x, then it would make it thinner. If it was 5 over x, that's something else entirely, and we're not ready for that. Probably at this point. 5 over x is technically it's 5 with an x to the minus 1, and then we have to deal with a negative exponent, which we are going to do that at some point, but let's do it in pieces. How's that? So far, so good? Okay, let's keep moving here. You could get asked to try to write an equation that fits some points here. So I could give you a picture of a graph here and say, well, let's write an equation for it. So using our knowledge, it's going to be y equals, there's going to be an x up in the corner. Anyone have an idea what the base of this thing logically should be? If it goes from a 16 to a 4 to a 1. What'd you say?
4.
Well, if you do 4, 4 means it's going to go up. But again, 2 is going to make the graph, like if I put a 2 right here, it's going to make the graph go upwards.
Negative half. 1/4.
A quarter is what I was hoping for. If you make it 1 over 4, wouldn't 1 over 4 mean that you're making it go downward, decaying? Does that make sense? Do we need to put like a plus number afterwards?
No.
0, technically. The asymptote's at 0. Okay. And then for your number in front here, I would say we probably don't need to put a number there because, like Sean just said, it went through 1. So maybe a 1 would fit right there. So hopefully this is the graph of y equals 1 times a quarter to the x. But I would say in terms of steps you're looking for, you got to first figure out like what the base should be, what the leading number in front should be. Do you need to mess around with the number afterwards to change the asymptotes around? So this one's pretty straightforward, though. It wasn't a really challenging one. Okay, last one. I've got a whole bunch of little pictures here to kind of describe to you some steps you can use in your calculator. There is another way that you can actually use your calculator to get an equation. I'd like to show you that now. Can you guys find the button Stat right here in your calculator? Okay. It's going to have a screen that looks like this one right here where it says Edit, Calculate, Tests, Edit, Sort A, Sort D. Okay. We want to go to 1. We want to edit. And what it's going to do is it's going to pull up what's essentially an XY table of values. Only it has, rather than X and Y, it has L1 and L2. I've shown a few of you guys this at some point before, maybe. Okay, Stat, and then Edit. And hopefully you can get to the screen here. What I'm going to do is I'm going to actually plug in points. I'm going to plug in -2, then -1, then 0. And then over in the other table, I'm going to plug in 16, 4, and 1. By the way, those were the points off of that graph I just showed you a minute ago. Okay. Everyone okay getting that typed in? Okay. If you go to y equals and like take out all your old graphs, what we're going to do is I'm going to show you how to make those points show up on a graph. You have to go up top though, and you see how up here there's plot 1, plot 2, plot 3? You have to press enter and embolden plot 1. By the way, when you're done doing this, take off the boldedness of plot 1 because it's going to screw things up otherwise. And now if I go like say zoom 6 to get a picture of a graph, you see how like there's a dot right here and a dot right here? I believe there's actually another dot. It's just way off the screen here. You can actually get your calculator to plot individual points. Further to that, your calculator is powerful enough that if you have 3 points, it can actually make an equation for you. I want to show you how that works. So to do that, go back to Stat. However, on this symbol right here, you see how Edit is what was currently emboldened? We need to go over to Calc, and we're going to calculate what's called an exponential regression. Exponential regression, just so you guys know, is actually way the heck down the list. It's at 0. So you're going to go X regression. Now, depending on your calculator, it might take you to a different screen than mine does. Okay, so if yours has some different lists, what you need to do is you need to tell it where to look for data. You need to find data in list 1 and list 2. And some of your calculators probably default to that already. So if yours does that, leave the first 2 things as L1, L2. If your calculator looks like mine, you need to go second and then the number 1. And the reason why it's number 1 is hidden behind the 1 is literally, it says L1. So I'm telling it, find some data in list 1. And then I have to put a comma. And then I got to go second, L2. I have to tell it where to find data. Some of your calculators probably it defaults to L1 and L2. It's the next step down that's important. We need to tell you where to put that data when we're done. And this is the most complicated one to find regardless of whose calculator you've got.
What did you put in for L2?
Second and then 2 is where L2 is. Okay. I now want to throw in y. Because what I'm going to ask it to do is I'm going to ask it to put an equation into y equals. Okay. Here's where you find y. It's a lot. Okay. Over here it says vars. Vars stands for variables. Then it either gives you vars or y vars. We would like a y variable. Oh, so for the other one, store reg equation. You actually can skip the third one and go right to there. So then from here, press vars. Now you're with me. So press vars, that's a variable. Then go over to y variables. We work with functions, so 1. And what it's going to do is it's just going to give you a list of all sorts of different y's.
Oh, these are your y values.
These are the y's that you know how when you make an equation? These are the y values in the y equals screen. So I don't care which one you pick. I'm going to pick y3 just to make a point. But you pick whichever one you want.
Okay. So that's the same.
What this is going to do, what I've now told my calculator to do, is make an equation that looks exponential. And the equation should pull data from list 1, should also pull data from list 2, and when you're done, I want it to make the equation show up in the third y slot. Now I'm going to press enter. this is less relevant. Go to your y equals screen. In the third y slot, magically, an equation just showed up. And the equation I got has a 1 in front and a 0.25 to the x. If I then graph this thing, it should actually show the graph going through those points. Who didn't get that to work? Let me help troubleshoot. Okay. So you need to go stat, calculate, exponential regression. Your L1 and L2 just come free right now. So you need to go down to store your equation. It's going to tell it where you want it. So vars, variables, y variables, work with functions, pick one, and then calculate. It's going to give you an equation, and that equation is now going to show up down there.
Okay.
Does that make sense?
Yep.
Okay, so your L1 and L2 show up anyways, so you just need to go to store reg equation here. We need a variable, we need a y variable, we work with functions, we want any of the y's. And we'll calculate it.
Yeah.
And then if you go to y equals, it made an equation there for you. It made the exact equation we thought it was going to be. Anybody else?
Yeah.
Okay.
Yeah.
Okay. Okay. So for you right here, the last thing you'll need is a variable, a y variable. We work with functions. You want to just pick one of these. I'll make 2. Okay, you then go to your y equals screen. There's going to be an equation sitting there. Okay. Anybody have issues with that? Because I want to get to this last example so we can call it a day. Sorry, this lesson is a lot longer than I thought it would be. Here's the example I want to give you then. You might get given, boy, that was a poor grammar. You might get given a table. Okay. Here's a word problem. They recorded bear sightings over the last 9 years, and as you can see in the data, the number of bear sightings seems to be going up. Does that make sense? Apparently it's going up exponentially. We'd like to make an equation about this, and then we want to determine when will we see 200 bears as the pattern continues. So in order to do this, we need to be able to type data into our calculator. So to do that, go stat, edit. Everybody okay to get back to there? Well, we now need to write over top of our previous data. So I need to go say 2006, 2007, 2008, 2009, 2010.
Do you have to do all of them?
I'm going to have to, yeah. 2011, 2012, 2013, and 2014. Okay, that's my X list. Then I have to go over, and I have to type in how many bears there were in each of those years. So actually, oddly enough, 16 is already in the right spot. And 18, 21. You guys okay being able to get all this data typed in? Yeah. Call me over if you struggle, okay? Just gonna kind of leave you for a bit then. Your calculator, being a machine, needs you to type in all of the data it needs properly. The point I want to make here then is that if you have two lists and one list is longer than the other list, your calculator can't reconcile that. So absolutely make sure that the 2014 and the 64 are ending. Because if you accidentally have one number further in one of the lists than the other, your calculator will say, what's up, I can't do this.
All staff, could we please have you log out of Power School? They are going to restart the server, so please log out of your Power School and we'll let you know when you can log back in.
Okay. Is everybody okay with this so far? Okay. So what I would say then is once you have your data, maybe go to your window. Now I want to try to change our window size up a little bit because from 0 to 10 is not really going to work. What is X referring to? Okay, well if I do year 0, that's literally year 0, the year of Christ kind of year, right? So we should start at maybe 2000. And maybe I should end at 2050 maybe? I don't know. Taking a guess as to how much X value to use. Your y value is how many bears we saw. Sure, that's a good low number. I want to make my high number be at least 200 because that's actually the question. The question is when will we get to 200? So maybe I'll go to 210. One more thing, go back to your equation and delete that old equation. We don't want it. But do make sure the plot is on up in the corner. And now we can graph. And what you should see is a whole bunch of points, hopefully, like this. Is everyone able to get a whole bunch of points like that? Yes? Oh, you have your x's and y's backwards. It's x is time and y is theirs. That's why. Drina? Oh, for the exponential regression.
Yeah, I think that is.
Okay. Okay, I remember why this works here. The reason why the overflow is happening is because your calculator is trying to calculate from year 0, again, like literally like year 0 on our calendar, all the way up to year 2000, and it's struggling to do that. It's too many numbers for your calculator to handle.
How do you give it a parameter?
Okay, so I'm going to change your data here. Let's go back to stat and edit. And you know how we were starting in the year like 2006, 2007, 2008? Why don't we just start with 6, 7, 8? Does that make sense? Because otherwise your graphing calculator is trying to work all the way back to literally year 0. That's having a hard time doing that. So change 2006 to just 6 and 7 and 8. Yeah. Well, technically 0, but yeah.
So what's our windows again?
Okay, so then for our window, rather than starting in the 2000s, we need to go to our window and make it go from, like, say, 0 to 50, I guess. So let's say that you get an answer of 49. Just keep in mind, 49 then is the year 2049. Does that make sense? So as I graph this guy again now, everyone okay getting the exponential graph?
Mine still looks the same as before.
It should. It's just rather than this being 2000 and 2050, it's actually just 0 and 50. So go to stat, go over and calculate. We need an equation, which is an exponential regression.
You can just press 2.
You could, yeah. Then depending on how your calculator works, tell it first where to find its data, and then lastly, tell it that you want it to be an equation in one of the y slots. I don't care which one slot. What should happen after you do that, when you go back to your graph, you should see an exponential graph going right through those points, hopefully.
Sorry. Okay, I just lost at L1 and L2.
Okay.
Where do I get the Y?
Bars. So one comma, then a variable, a y variable, function, and we'll just pick that one, and then press enter. Okay, whatever. Can you give me 2 minutes? I'm almost done here. Okay, our goal is to figure when we'll get 200 bears. Well, to do that, make y also equal 200 and intersect and find when it finally will equal 200 bears. Okay, if you do get it to work, let me know. If you can't get it to be 20.31.
Mine works.
Okay, dimension mismatch usually means that for all your data here, see how this one went to 64? This one went to 14 there. You missed a number. See how you went to 10? That's what dimension mismatch means. It means that your data is not where it's supposed to be. Now it should work. So if we try this, we graph it, we should get a whole bunch of points. We should get a line going through it. Put a 200 up there and intersect. Was everybody able to get like 20.3 if you're trying it for x? So that would mean that this would happen in the year 2030. No, 2020. Sorry. Yeah, 20.31859. Yeah, so it's going to happen in the year 2020. Midpoint 3 would mean March of 2020. Any questions on that? Okay. If you guys have your assignment nearby, that's how you solve question 9 on the assignment, by the way. I've only seen this come up once in like the last, since I've been teaching. It came up once. It's not something that likely is going to happen, but in case it does, I want you guys to know how. So. We're looking for when it equals 200 bears. So we went to y equals the equivalent of 200. And that's where it's going to equal 200 bears. Intercept. Okay. You guys have any questions? Okay, so a quick recap. Sorry, I know I'm rushing here. You guys need to know what these graphs look like. To be honest, that's the easier outcome. The harder outcome is, can you solve a problem involving logs or exponents? We'll do logs eventually. So. Questions, comments, concerns, conundrums, curiosities? Okay, cool. Sorry that there's only a little bit of time left today. This took way longer than I thought it would. I'll stop the recording now.